Good morning. I'm Josh. I'm completing a PhD at the University of Washington that involves seismology, glaciology, and signal processing within the Department of Earth and Space Sciences. My co-author today is Kate Alsat, who is also within the department and with the Pacific Northwest Seismic Network. Today I will summarize a detection methodology that we have developed to increase the detection capability of two simple but very common seismic event detectors. I will introduce two concepts that we have implemented to improve these detectors. One of these concepts is objective thresholding via Neyman Pearson hypothesis decision theory. The other concept is effective dimension estimation. Objective thresholds allow the detection performance of a given detector to be quantified in terms of the expected number of false detections and the expected number of true detections. Effective dimension estimation improves the confidence we place in our hypothesis testing on the presence or absence of a target waveform. I begin with a problem currently confronted by the Pacific Northwest Seismic Network. This plot illustrates a helicorder, which allows a seismologist to read a seismic record from the channel of a single geophone over time, left to right, and then down like a book. During a typical day, each station on one of the Cascade volcanoes detects several thousands of events according to a digital energy detector. A subset of those detections are shown here in red. This detector makes a decision about the presence or absence of a seismic signal based upon a statistic computed from the data and a threshold from the statistic. Oftentimes, manual review will demonstrate that this event pool consists of a large number of false alarms on noise or wind, for example. To avoid using these false alarms in further processing, as in waveform matching, they must be manually removed from the event pool. This consumes both computational and human resources. A different problem exists on the Greenland ice sheet. In this case, the very presence of narrowband signals that may be non-geophysical in origin dominate the wave field. This figure illustrates a spectrogram computed from a geophone on the West Greenland ice sheet at about 69 north and at about 50 west. The bright horizontal lines indicate a source of high-power monochromatic energy. Because the waveform data appear mostly emergent, it is difficult to detect transient events without further processing. It is visually unclear if each energy burst is a transient signal or not. We would like to be able to detect transient events in the presence of what I'm calling here interference. These previous two examples illustrate common problems in seismic monitoring scenarios. The first problem concerns false alarms. In this case, detection thresholds that are lowered to improve detection rates are often subjective. Lowering these detection thresholds simultaneously increases false alarms. The second problem has to do with structured noise. Both processing and the geophysical environment can be sources of temporally correlated noise, and this can invalidate the assumptions made on the statistical properties of the data. It can lead to incorrect interpretation of cross-correlation and may increase false alarms and misdetections. I will propose two partial solutions to these problems. In the first solution, I apply an optimal decision rule for signal detectors called the Neyman Pearson criteria. This decision rule maximizes the probability of detection of a given class of signals at a given false alarm rate. In the second solution, I introduce an estimator to account for the correlation structure introduced by effects like filtering. This provides an estimate for the effective number of degrees of freedom in the data and provides the applicability of hypothesis testing. Each of these solutions provides two primary advantages. First, they are demonstrably effective at increasing detection rates, but only require estimating two parameters. Second, by selecting detection thresholds according to a constant false detection rate, an expected number of false triggers in any detection scenario can be anticipated. The first detector I consider is the energy detector. Seismic energy detectors require almost no information about the signal aside from its expected temporal duration. Rather, they determine the presence or absence of statistically significant increases in data SNR, or signal-to-noise ratio, according to a prescribed decision rule. A challenge associated with their implementation arises when the background noise at the observing geophone is temporally correlated. This reduces the effective degrees of freedom in the data. My solution to this problem requires estimating these effective degrees of freedom and including this estimate in the anticipated probability distribution for the data. The second detector I consider is the correlation detector. In contrast to energy detectors, seismic correlation detectors require almost complete information about the signal. They determine the presence of a signal according to an estimated correlation coefficient and a prescribed decision rule. A challenge associated with their implementation arises again when the background noise at the observing geophone is temporally correlated and thereby reduces the effective degrees of freedom in the data. In an autonomous detection scenario, I will demonstrate how to maximize the degrees of freedom of the template signal when these templates are constructed automatically from mutually correlated families of waveforms. I will first review the STA-LTA detector, which is the most common energy detector implemented in seismology. The STA-LTA detector compares estimates of average energy content in two non-overlapping windows of seismic data. First, the sample variance is computed in the leading window that is indicated here by the black portion of this example signal. Second, the sample variance is computed in the following shorter window, indicated by the red portion of this signal. If a signal is localized in the following window, this ratio will be larger than it is in the presence of just noise. Because each sample is the sum of signal and noise, this STA-LTA statistic has a probability density function. In this case, it follows a non-central F distribution. It is parameterized by the size of the front and back window and a non-centrality parameter that is proportional to the signal-to-noise ratio in the data. Because STA-LTA statistics are random variables with known probability density functions, this PDF can be integrated over a threshold-dependent region to assess its detection capability. The choice of this detection threshold will have an obvious effect on the true detection and false detection rates. In this illustration, I have not included the derivation that demonstrates X, the STA-LTA statistic, arises from the ratio of two maximum likelihood functions. That exercise is important, and I provided a reference by K at the end of today's talk that includes a similar derivation. I will now continue with the development of the decision rule. In this figure, I illustrate the PDF for the STA-LTA statistic when, under the two competing hypotheses, signal present versus signal absent. Under both hypotheses, the short-term window and long-term window lengths are fixed. Under the alternative hypothesis that a signal is present, I use a unit SNR signal, which means that the non-centrality parameter of the non-central F distribution is equal to the short-term window less 1. The low SNR of this hypothetical signal induces considerable overlap between the two PDFs. A decision rule chooses between these competing hypotheses based upon the size of the STA-LTA statistic, again what I'm calling here X, relative to a threshold value. The detection capability of this energy detector for the unit SNR signal is then computed by integrating the alternative PDF over what I am calling the acceptance region. These are values of X greater than the threshold value. The false detection probability is similarly computed by integrating the null PDF over the acceptance region. This gives the probability of making a decision that a signal is present when in fact just noise is present. In a given monitoring scenario, one desires to maximize the probability of detection of a given signal when the false detection rate is known. To do so, I apply a detection rule known as the Neyman Pearson criteria. This criteria states that for a fixed probability of false detection, the true detection probability, using this sufficient statistic, is maximized if the decision rule threshold value is selected to satisfy the fixed false detection constraint. Once the false detection rate is set, the corresponding threshold value that provides the false alarm rate can be inverted from the null hypothesis cumulative probability density function, or CDF. This threshold value then maximizes the detection probability of the signal. The acceptance region, detection threshold, and sufficient statistic X together constitute the Neyman Pearson STA-LTA detector. It is optimal in the sense that it maximizes the detection probability for a given false alarm rate. An obvious question that follows this formulation is this: does this work on real data? This figure displays a null distribution for the STA-LTA statistic using real detection parameters that I selected to pick out ice quakes that originate from the Greenland ice sheet. I have assumed that the noise field is white Gaussian random process. The gray histogram provides the observed distribution from several hours of seismic noise recorded from the vertical component of an L28 geophone. It is immediately obvious that these two distributions do not agree. The variance in the observed distribution is considerably larger, with considerably more area under the right portion of the tail. What this means is that some aspect of our statistical assumptions were incorrect. The primary error here is that I have assumed that the degrees of freedom in the data equate to the data length, as in the case of the independent identically distributed Gaussian noise. However, temporally correlated noise that is present in the data or pre-processing operations can reduce the effective degrees of freedom. Therefore, the distributions under the competing hypotheses both behave as though fewer samples are present. It is necessary to compute the dimension reduction in order to get the hypotheses and the underlying distributions used in the decision rule correct. This requires forming an estimator for the effective degrees of freedom, NE. Wachecki-Vergara et al. Provided such an estimator for NE in a 2001 technical report. I provide a slight adaptation of that estimator here. This estimator uses a relationship between the effective degrees of freedom in the data and the variance of the sample correlation random variable that is computed from pre-event noise. For the STA-LTA energy detector, a noise vector is divided up into hundreds or thousands of windows, each with a length equal to that of the LTA window length. The sample correlation between each window is then computed, and this forms an empirical PDF for the sample correlation in the presence of the observed noise. An identical operation is performed using the short time windows, consistent with the length of the STA window. The population variance of each sample correlation is inversely proportional to the number of degrees of freedom in the data. However, we do not have access to the population variance, so we instead compute the sample variance. The sample variance is therefore computed for both short window correlations and long window correlations, and the estimated degrees of freedom in both windows can be explicitly solved. Stated differently, I estimate the effective short time window and the effective long time window lengths. I implement this process automatically in our detection algorithm. I will use this estimator again when I review correlation detectors. However, in the event that this estimator has poor performance, I also estimate NE from the observed STA-LTA distribution directly. To compute an alternative estimator for NE, I also invert the first two null hypothesis F distribution moments for their degrees of freedom. This estimator uses the sample mean and sample variance computed for the STA-LTA statistic on the data. The corresponding effective degrees of freedom for each window are again estimated by solving these moments for L and S. With these two estimated pairs available, I use a pair of estimated degrees of freedom that best fits the observed data. The best fitting pair then parameterizes the distribution under each hypothesis. In this example, the hypothesized null distribution and the observed null distribution now agree very well. The reduction in effective degrees of freedom was considerable relative to the naive distribution. In particular, the short time window had an effective length of 4, although the short time window length was set to 160 samples. This example was not cherry-picked for this talk. Rather, this improvement in the corrected distribution fit was relatively common. To view the parameterized alternative distribution, I have added a reference arrow in blue here to the right. This figure compares the competing distributions. I have computed the alternative using a unit SNR signal again, with the same effective degrees of freedom. To maximize the detection capability of a signal, I fix the false alarm rate at a constant value of 10 to the minus 3 and invert for the threshold value. This gives the acceptance region, and the area under the curve of the alternative distribution shown here provides a detection capability. Of course, a higher SNR signal would have a larger STA-LTA value and therefore a higher detection capability. It would have a more peaked distribution with more tail area to the right. My co-author Kate has tested the adaptive detector that we have developed against a hard threshold non-adaptive detector. This figure illustrates the results of the test that compares hand-picked events with both our adaptive detector and the non-adaptive fixed threshold detector that we previously had implemented. Kate compared the detection performance for the adaptive detector under distinct false alarm rates in blue against the detection performance of the adaptive detector under distinct threshold values in red. Consider first the highest false alarm rate case. Here the adaptive detector picks nearly as many of the true events as the non-adaptive detector, but with fewer false detections when compared to hand-picked events. In addition, the adaptive detector correctly picks more events for the two lower false alarm thresholds. Overall, the adaptive detector demonstrably outperforms the non-adaptive detector when both true events and false alarms are considered. This summarizes our treatment of the STA-LTA detector. I will now move on to the correlation detector. The correlation detector is on the opposite end of the detector spectrum in terms of signal knowledge. Whereas the energy detector statistic identifies any increase in SNR, the correlation detector identifies matches of a data stream of a particular template signal. In this example, I have shown the three-component record of a transient microseismic waveform observed from the Greenland ice sheet. The similarity between the waveform pairs are quantified according to a correlation statistic. However, this correlation statistic is only meaningful if chance high correlation values are small when only noise is present in the data stream. The chance of spurious high correlation values and pure noise increases as the degrees of freedom in the signal are reduced. Therefore, it is more appropriate to consider the correlation coefficient as being a function of both the effective degrees of freedom in the data stream and the population or true correlation. In this figure, I provide an illustration of the effect of waveform duration and temporally correlated noise to demonstrate their combined effect on sample correlation. The middle left red time series shows a contrived, short-length template waveform. In the trace above that, a contrived seismic event with white noise is added to it. The bottom left trace illustrates the template with bandpass filter noise added to it. I have adjusted the variance of the added noise in both cases to equalize the SNR of the signals. On the top right, I have computed 5,000 sample correlations for a set of 5,000 hypothetical repeating seismic events who have traces like those on the upper left. On the bottom right, I show 5,000 sample correlations for a set of 5,000 hypothetical repeating seismic events with traces like those on the bottom left. It is immediately obvious that filtering of the additive noise effectively increases the variance of the correlation distribution. If I now select an arbitrary threshold for match declaration using the correlation PDF in both cases, and integrate the left area of each distribution, I obtain the probability of missing a detection. It is qualitatively obvious that despite the same SNR, I miss considerably more multiplet events if the target waveforms are embedded in temporally correlated noise. Therefore, we must account for this reduction in detection capability. As with the energy detector, the detection of a target waveform is determined using a binary hypothesis test. This example shows the distribution under the null hypothesis and alternative hypothesis in the case that the data windows are only 20 samples long. As with the energy detector, the probability of false alarm and the probability of detection are evaluated by integrating each distribution over the acceptance region using a given decision rule threshold value. I have plotted both the decision rule threshold value and the population correlation using the signal present hypothesis. In this example, the correlation value of the population is about 0.7. Again, I implement the Neyman Pearson criteria and choose a decision threshold to satisfy the false alarm constraint. In this case, the sample correlation is the sufficient statistic which can be derived by considering each sample of x and w to be drawn from a bivariate distribution. In this example, I choose a very large false alarm rate of 10 to the minus 2 in order to illustrate the decision rule geometry. I then invert for the corresponding threshold eta that gives the fixed false alarm rate, and then use this threshold value when making a decision on the presence of the target waveform after computing the sample correlation. Because the signal duration here is short, the detection performance is poor despite knowledge and usage of the Neyman Pearson criteria. This figure illustrates the effect that shortening signal duration has upon sample correlation value. Each pair of curves in this figure gives a null distribution and the alternative distribution for the waveform absent versus waveform present scenarios. Again, I have used a population correlation of about 0.7 under the waveform present or alternative case. The applicable distribution pair using signals with an effective data dimension of only 10 is shown by the thick dash curve. It illustrates that there is considerable overlap between the alternative and null distributions. The case where the effective data dimension is 50 demonstrates considerably less overlap. Therefore, the detection performance is significantly improved if additional waveform samples are available. For a fixed detection performance, or equivalently fixed integration area, the decision rule would have to increase as NE decreases. To illustrate the relationship between the threshold and effective dimension, I have considered curves of constant detection capability. These curves are parameterized by the decision rule threshold and effective dimension. In this case, the population correlation is again fixed as 0.7. Take, for example, the leftmost curve. Each point on this curve gives the effective dimension and decision rule threshold pair that are required to constitute a Neyman Pearson detector with a detection capability of 99%. If NE is 20, for an effective 20 sample length signal, then eta, the decision rule threshold, must be less than 0.35. This low value leads to very large false alarm rates. If I had instead 100 samples available, the threshold value for event declaration can be increased to well over 0.55, but still provide a 99% detection capability. The right curves similarly provide points of eta and NE that provide points of reduced detection capability. Moving left to right across each curve decreases the false alarm rates and can be thought of as increasing data length and threshold pairs to maintain detection performance while simultaneously reducing false alarm rates. The correlation test is complicated when knowledge of the template signal is incomplete. We currently have an autonomous multiplet event detector implemented to detect repeating events which proceeds with an initially unknown template signal. Rather, this detector automatically identifies template signals based upon mutually well-correlated repeating waveforms that have been initially identified using an STA-LTA detector. First, the energy detector identifies an event pool of waveforms. Next, these events are correlated together post-detection. An initial correlation value is then prescribed based upon the sample length of the data. If n events with n waveforms all mutually correlate initially above a threshold value, this constitutes a waveform cluster. This is equivalent to a complete link clustering algorithm. The set of n waveforms may then be considered to be a multiplet family. A positive linear combination of the waveforms then provides a representation for that family. This waveform representation, which is built from the stacking, is in a template event. I place the question of how to initially assign a correlation value for the clustering aside. Instead I ask, can I come up with different values of lambda or stack weights, all positive, to maximize the effective data dimension? This figure illustrates how weight choice matters. The bottom red curve illustrates a signal. The traces above are a sum of this signal and noise. The first 6 are a sum of the red signal and white noise. The next top 6 only have low frequency bandpass filtered noise added. I have equalized the noise variance so that each dark signal has unit SNR. Because the top traces have additive filtered noise, they have a reduced number of degrees of freedom relative to the white noise traces. The objective here is to add these signals together to maximize the effective degrees of freedom NE. To maximize NE, I can equivalently minimize the variance of the sample correlation PDF between a hypothetical template and noise sample vectors. Recall the estimator that I used to obtain NE for the energy detector. I previously illustrated that the number of degrees of freedom in a signal is inversely related to the variance of the sample correlation PDF for the pre-event noise. In the original form of the Wychecki-Vergara estimator, a template is correlated with pre-event noise samples in many independent noise windows. The top left equation here gives a sample correlation in window K of noise vector WK with a hypothetical linear combination of waveforms. The columns of matrix U are formed from mutually correlated waveforms in a given cluster. I have pictured a hypothetical stack of these waveforms on the right, which is given by U times lambda. To compute the weights given by the vector lambda in practice, I again compute the sample correlation between this hypothetical stack and a hypothetical noise vector. Some algebra illustrates that the sample correlation can then be written as the equation on the bottom right. It has the form of a generalized eigenvalue problem with a positivity constraint on the weights. For stability reasons, it is better to invert for lambda using the reciprocal of the variance, since lambda may be in the null space of U if it does not have full rank. The inversion itself requires implementing the positivity constraint and can be done with the optimization toolbox in MATLAB. I show how that weight choice affects the detection performance of a sample correlation in this figure by comparing two weight choices. I have inverted for the optimal weight choice to make a template from the cluster waveforms. For comparison, I have also added cluster waveforms linearly. The top plot illustrates the null and alternative distribution pair when the correlation detector template is computed using the optimal NE stack. The bottom illustrates the same pair with a simple linear or average stacking. These detectors have the same fixed false alarm rate constraint of 10 to the minus 3. The primary difference is in the effective degrees of freedom in the template signal. The top case has a detection capability of 0.77, whereas the bottom linear stack forms a correlation detector with a detection capability equal to that of flipping a coin. Each detector has the same false alarm rate, therefore the top detector from the optimal stack demonstrably outforms the bottom detector using a template computed from the usual equal weighted simple stack. I have not yet determined if the stack SNR is improved with the optimal case, as it may not be. In that case, there may be a trade-off that can be further improved by simultaneously increasing the SNR of the stack and NE in some respect. I'm now going to summarize the results of improving these end-member seismic detectors. First, I review the challenges with current detectors implemented at the Pacific Northwest Seismic Network, then the solutions, and finally their practical implementation. Challenge 1. Detector thresholds that are set too low to obtain additional detections will increase false alarm rates. Challenge 2. Pre-processed data in natural geophysically occurring band-limited noise may reduce the signal's degrees of freedom and thereby lead to incorrectly hypothesized distribution for detector statistics. One solution to these challenges requires estimating the effective dimension reduction using an estimator either based on sample correlation of the noise or, in the energy detector case, moments of the non-central F distribution. A complementary solution maximizes the detection capability for a given detector and fixed false alarm rate by implementing an optimal decision rule called the Neyman Pearson criteria. These comparatively simple solutions have several advantages. I have listed 2 of them. For monitoring scenarios at the PNSN, the improvement for both the energy detector and the correlation detector with a fixed false alarm rates allows a manual reviewer to select the number of expected false triggers to review each day. For multiplet detection, the performance of a correlation detector that uses a correlation template built from clustering can be optimized by maximizing NE. Cumulatively, these simple improvements to detectors are being implemented at the PNSN and on an ice sheet monitoring project in western Greenland. Kate Allstat, again my co-author, has a website running that contains some preliminary results. The username for this website is Bob, and the password is letmein, all lowercase, all one word. Finally, it's important to give credit. The Wachecki-Vergara et al. Paper provides a very rigorous analysis of correlation detectors and the effective dimension reduction that results from processing or noise coloration. A great text on detection theory is given by Stephen K. It includes energy and subspace detectors primarily. I've used some illustrations from David Harris's technical report on subspace detectors that are implemented currently at Lawrence Livermore National Lab. All the figures in this talk were created using MATLAB and a function called export fig from the Central File Exchange, in addition to being edited with text using PowerPoint. The data I used came from a NASA and NSF-funded project with Ian Jockin, Sarah Doss, and Mark Ben. Seismic waveforms from the PNSN database came from Kate Allstat. Finally, I had a very constructive correspondence with Stephen Gibbons from NORSAR on effective data dimension and network signals. Stephen is also a very prolific scientific writer and specializes in seismic detection. David Harris, who was formerly at Lawrence Livermore National Labs, provided feedback on correct implementation of the Wachecki-Vergara estimator. Don Percival at the Applied Physics Lab provided some input and time on discussion of optimizing degree of freedom for waveform stacks. Thanks